Yes, so let me start with a brief introduction into infinite Metroid theory. I start first with some simple examples of infinite Metroids, some very natural examples that follows easily from knowing the finite Metroids. So for example, if we have an infinite graph, then we can define the cycle Metroid of this graph in the same way as in the finite case. If you have some vector space, possibly infinite vector space, then and we take some subset of it, then these vectors with the linear independence define a Metroid. And if we have some infinite sets and we declare independent those subsets that has size at most n, for some natural number n, then this is a infinite uniform Metroids. So what kind of axiomatization can we give for these kind of infinite Metroids? So let's do this first attempt. The first two axioms are not a big surprise. In the augmentation axiom, we demand it only for finite independent sets. And we have an extra axiom that tells that if we have some set and every finite subset of this set is independent, then the whole set is independent. Let me tell also in the same axiomatization in the language of circuits, it will be even more obvious that how close is this for the finite Metroid theory. So we have basically the usual axioms for finite Metroids, and we have an extra axiom that all the circuits are finite, and we drop the assumption that the ground set is finite. Okay, so Rodó pointed out in the 60s that this kind of infinite generalization of the concept of Metroids is not entirely satisfying, because duality is one of the most important features of infinite Metroids, and so one can see that if we take the subset of the edge sets that are disjoint from some base according to these Metroids that we just axiomatized, then this doesn't form a Metroid usually according to this definition. And to fix this problem, Rodó initiated a program to find the right infinite generalization of Metroids. So what do we mean about right infinite generalization? There are some natural requirements that we want to satisfy. We want the usual axioms for finite Metroids to be true, where the augmentation axiom is restricted to finite independent sets. We want that every independent set should be extendable to an inclusion-wise maximal one, and every dependent set should contain a minimal dependent set. In other words, we want bases and circuits. And we want that duality and minors should work in the same way as we expect from the finite theory. So the formal definition of duals and minors give Metroids. Okay, in the solution of Rodó's programs, there were several attempts. I will tell the three main steps that led eventually to the infinite Metroid concept that we do have nowadays. So Higgs found some class of structures that he called the B-Metroids. And he didn't have an axiomatization for these, but so these satisfied all the requirements that we listed. Then Oaksley gave an axiomatization for B-Metroids and proved that this is actually the largest class of structures satisfying all the requirements. And eventually, Brun and his co-authors find cryptomorphic axioms that generalizing the usual different kind of axiomatizations of the finite case. Okay, so what are these axioms? In the language of independent sets, the first two axioms are not a big surprise, but the third axiom is already a little bit tricky. So in the augmentation axiom, we demand only this augmentation property in the case when we have two independent sets, one of them maximal, the other one is not, then the maximal one can give an edge to not maximal one. And the last axiom says basically that every minor has a base. So for every subset of the edges, subset X of the edges, every independent subset of X can be extended to a maximal independent subset of X. And after having this more general Metroid concept, we can, a short remark that finitary Metroids are, so we define finitary Metroids as Metroids having only finite circuits. And the naive axiomatizations that I showed at the beginning are exactly the axiomatizations of finitary Metroids. Feel free to stop me anytime when you have questions. Okay, let's see some examples. What kind of Metroids do we have with having this more general Metroid concept? So we have topological cycle Metroids, which as far as I know was the main motivation in 2010 in the solution of the Rado program, so in the last phase of the solution of Rado's program. So let G be a locally finite connected graph. Locally finite means just that every degrees are just finite. And let's take the Freudenthal compactification of this G. So we can imagine this graph as a one complex. So the edges are homeomorphic copies of the 0-1 intervals. So this is a topological space, and then we can take the Freudenthal compactification of it. And let us call the homeomorphic copies of the unit circle in this topological space the cycles of this space. I don't know the history of this notation, so one shouldn't confuse it the size of the graph G, but it's denoted like this always. And in this case, the edge sets of these cycles, these topological cycles, are the circuits of a Metroid. So one can prove this. And actually the dual of this Metroid is the so-called finite bond Metroid, in which the circuits are simply the finite bonds in the graph. Okay, another example is the so-called thin-sum Metroids. We take a field F and the set A, and we take a subset of functions with domain A and range the subset of F in such a way that for every particular element of A, there are just finitely many functions that has a non-zero value at this X. And in this case, an infinitely linear combination of these kind of vectors can be easily defined, because if we take formally a linear combination, then at every coordinate, we have just finitely many non-zero elements, and we can take easily the sum. And so this gives a Metroid, and it gives the opportunity to define representability for Metroids having not just finite circuits. So the usual representability can handle only Metroids with only finite circuits. but this thin sum representability concept generalized this. And last but not least, uniform metroids. It's not entirely trivial how to define at all uniform metroids in the infinite case, because, for example, saying that I want all the countable infinite sets bases, it doesn't work, because if we kick out an element from a countable infinite set, then it is still countably infinite. So that's not the right way to define it, but there is the definition. So for every, we demand that whenever we have an independent set and an edge in this independent set and another edge which is in the complement, then if we delete this edge and put the other edge to I, then this should be independent again. So this this concept was discovered by Bowler and Geschke, and it has a big importance in relative consistency proofs. So there are several interesting statements in infinite metroid theory that there is a proof for some kind of well-behaved subclass of metroids, and we can prove using uniform metroids and some set theoretic assumptions that that it cannot be proved for all metroids. Okay, so these examples getting richer using the more general metroid concept. I wanted just to show that. Okay, so let's turn to the metroid intersection conjecture. This is a conjecture of Nash-Williams, and it is exactly the infinite generalization of the metroid intersection theorem of Edmonds, translating it using the combinatorial structure of the optimal solution instead of quantities. So it says that if we have two metroids on the same ground set, then we are able to find a common independent set that admits a bipartition, such that if we take the union of the closure of these two parts in the corresponding metroids, then it gives the whole edge set. Yeah, historically, Nash-Williams conjectured it with finitary metroids, so with the older infinite metroid concept. And there is a natural generalization simply replacing finitary metroids with arbitrary metroids. But yeah, it's wide open, so it seems very hard if true at all. So not so for some very special subclass of metroids, there are positive results, but otherwise we do not know much about it. Okay, so the augmenting path method in the standard proof of the intersection theorem of Edmonds, it's turned out to be a useful tool also in the proof of the infinite case, but it is insufficient itself to prove the theorem. So if we just iterate some augmenting paths, that then in the end there is no guarantee that we any kind of meaningful limit object have at the end. So so it's insufficient to solve the problem. Okay, let me tell some partial results. So if both of the metroids is a partition metroid, so a direct sum of one uniform metroid, then it is known to be true. And it is the so-called Koenig's theorem for infinite graphs. It was proven by Aharon, Nash-Williams, and Schella. And it's so in the language of graphs, it says that if we have a bipartite graph, then we can take always a matching in such a way that we can pick exactly one vertex from each edge of the matching, such that the resulting vertex set covers all the edges. And this special case is already a hard one, so it's like 30 pages and tricky. Another partial result was done by Aharoni and Ziv. And historically, the previous one was even before Nash-Williams conjectured this intersection conjecture. So, so technically, it's a special case of it. So the partial result of Aharoni and Ziv is that if the edge set is countable and one of the metroid is a direct sum of finite rank metroids, then the conjecture is true for these kind of metroids. And the result that I will tell you, or at least an overview about it, I will tell that if the edge set is countable, then the conjecture holds. Okay, so let M and N finite metroids on a fixed countable edge set E. And let me tell few tools that developed by Aharoni and Ziv already, or technically some of the tools were developed even earlier by Aharoni and Berger when they working on the so-called Erdős-Menger conjecture. There are some connection between the intersection conjecture and the Erdős-Menger conjecture. I will talk about a few words about it later. Okay, so one of the important notion is the wave. So if we have an ordered pair of metroids, Mn, then an Mn wave is a subset of edges such that there is a base of the metroid M restricted to W, which is independent in N contracted to W. One can show that the union of waves is always a wave, and eliminating waves and dealing with waves will have an important role in the proof. So let's call a wave trivial if it consists only M loops. It is then really a wave because if we choose B to be the empty set, then it obviously witnesses that this is a wave. And of course, the empty set itself is also always a wave. So definition, still Aharoni's definition. A wave is a hindrance if there is W is a hindrance if there is no M independent base of the N contracted to W. And we call an ordered pair of metroids unhindered if there is no such a hindrance. So the standard way to attack the intersection conjecture is a reformulation. It's through some reformulation discovered by Aharoni and Ziv. And this is the following. So if there is an M independent base of N, if and only if this ordered pair of metroids is unhindered. So this conjecture is equivalent with the Matroid intersection conjecture. Actually, even if the metroids are not finitary and the edge set has arbitrary size. So this is still true. Yeah, and being unhindered is obviously a necessary condition to have an M independent base of N, because if we take an arbitrary subset of W subset of the edges, maybe which is not necessarily a wave at all, not necessarily a wave, then if we have an M independent N base, then the intersection of B with W must actually must be spanning in N contracted to W and must be, of course, independent in M. So the necessity of the condition is obvious. The interesting part that if such a base do not exist, then this kind of abstraction can be found always like a wave. So in some sense, an extremal abstraction can be found always. Okay, so from now on, we assume that this pair is unhindered, and we want to find an M-independent base of N. And yeah, this is now the new part. So that was the end of the Aharon's if part. So let's call a common independent set of the two metroids feasible if, after contracting this common independent set in both metroids, the resulting pair is unhindered. And yeah, so the original pair is unhindered. It means that the empty set is feasible. It's just a small remark. And intuitively, feasible sets are exactly those subsets of the edge sets that can be extended to an M-independent base of N. But we know this just after proving the theorem, but it is, so that is our intention at the moment. Okay, in the countable case, the following key lemma will imply the theorem easily. So the key lemma says that whenever we have an unhindered pair of finitary metroids on a common countable edge set, then for every edge E, we are able to find a feasible I which spans this prescribed edge E in metroid N. So why is it true that it is enough to prove this lemma in order to prove the conjecture in the countable case? So suppose that we know already that this lemma true, and let us enumerate the edges. And we do a recursive construction. We start with the empty set, and in a general step, if the following edge in the enumeration is already spanned by ik in the metroid N, then we do nothing. If it is not spanned, then we apply the lemma after the contraction of ik and take simply the union of the resulting I with ik. So if some set is feasible with respect to this system, then it follows from the definition that the ik union I is also feasible with respect to the original. So in this way we really have again some feasible set. So we have some increasing sequence of feasible sets here, and if we just take the union, then it is of course a common independent set again. It is because the metroids are finitary, so there are no infinite circuits. So if this B would contain some circuits in one of the metroids, then this is a finite circuit, and for some large enough index k, ik would contain already that circuit. So in this step, we use that the metroids are finitary. And of course, this B spans every edge in the metroid N, because in the construction we do the construction obviously, and to achieve this goal. Okay, so if we can prove this lemma, then it will imply the conjecture in the countable case. Okay, we need a new definition. We call a feasible set nice if there is no non-trivial wave after contracting this set. And we need here some some technical lemmas as well. I will not go into the proof of them, just I will state them. Every feasible set can be extended to a nice feasible set. Yeah, so this lemma is based on the fact that if we have two finite matroids on the same ground set, and one of them have a base which contains the base of the other one, and vice versa, then in this case they have a common base. And so that's the main idea in the proof of this, the first lemma. Yeah, this statement is obvious for finite matroids because the conditions imply that the two matroids must have the same rank, and then when one of them contains a base of the other, then the two bases must be the same. But it is a non-trivial theorem for finite matroids, and yeah, and surprisingly, this is unprovable for orbiter matroids. So under some set theoretical assumptions, there is a counterexample. Okay, so the second technical lemma says that if we have a nice feasible set and we use the augmenting path method of in the usual standard proof of the Edmonds Metroid intersection theorem, then the resulting common independent set is still a feasible independent set. Still a feasible set. And the third lemma says that we can actually assume without loss of generality in the proof of this key lemma that the empty set is already a nice feasible set. So in other words, there is no non-trivial wave. Okay. Okay, so now this part of the proof is I think the key part. So these lemmas in this previous slide are mostly technical things. So now we take a enumeration of the H set again. So we want to prove now the key lemma. So let us recall that what was it? The key lemma said that we have this pair of matroids which is unhindered. So there is no hindrance, there is no wave such that no wave W in which we cannot find a set which is independent in M and spanning in N contracted to W. So we have an unhindered pair, and we want to find a feasible set which spans in N a prescribed edge E. Okay, so let's do the proof using these three technical lemmas. So we start the recursive construction with the empty set as earlier. We fix an enumeration of the edges and we order the edge set according to this enumeration. So in other words, we just take a omega type enumeration of the edge set. So for everybody there are just finitely many smaller. Okay, and we will define actually a sequence of nice feasible sets. So one of the technical lemma ensured that we may assume that the empty set is a nice feasible set. So at the beginning we are okay. And in a general step, we pick some edge which not spanned in our actual common independent set in Metroid N, and for which we have there exists an augmenting path in the sense of the proof of the usual proof of the Edmonds Metroid intersection theorem. And what do? We just use this augmenting pad P. One of the technical lemma in the previous slide told us that if we have a nice feasible set and we use an augmenting pad, then the result is still feasible. And one other technical lemma told that we can extend the feasible set to a nice feasible set. So we exactly do this to get the following member of the sequence. So to define I k plus 1. Okay, and so it's clear that actually, so this sequence, it's not necessarily, so it's usually not increasing with respect to inclusion, but it is easy to check that it's increasing in sense of the n span. So the n span of the ik sets are strictly increasing. And yeah, we claim that actually the union of all of these n spans is the whole edge set. It is enough if we manage to prove this claim, then we are done, because this edge E is in somewhere in E, and then already some of the ik spans it in N, and in the construction these ik sets are feasible sets. Okay, so let's see an overview of the proof. So we define this X, which we want to be the empty set, and first of all, we can observe. Okay, first of all, so we let X be the whole edge set minus this union. And we can observe first that it is not possible that this X consists of M loops, because according to the conditions, the MN pair is unhindered. So in particular, the set E minus X must span in N the set X, and because the metroids are finitary, so every circuits are just finite. So if we take an arbitrary element of this X, then there are finitely many elements of E minus X that spans this element. And if we can span everything, so we span everything out of X, then we can choose a large enough K that in the n span of this ik, these finitely many edges are already there, and then it shows that ik spans in Metroid and some element of X, which is impossible by definition. So X cannot consist of just M loops, and we define for every X, so we of course assume for a contradiction that this set X is non-empty. And for every element of this set, we define this EXK quantity, not quantity, edge set, EXK edge set. And this is the edges, so we take the auxiliary digraph from the Edmonds proof, so the finite case. So from the proof of the intersection theorem of Edmonds, and we have a sequence of auxiliary digraphs. So for every ik, we can build this corresponding d. I denoted it here like d, ik, and m. We can construct these auxiliary digraphs, and exk is the set of all elements of E that are reachable from X in this auxiliary digraph. Reachable from X in the auxiliary digraph. And one can show that these E, it's just some kind of some calculation. One has to analyze just how the structure of the auxiliary digraphs changing after using an augmenting path and adding new elements. So this EXK is it is growing in increasing in K, and yeah, so under the indirect assumption that this X set is non-empty, we can take, yeah, so there will be for every such an X, there will be some index that this X just stuck there. There is no, from that index, if we take an auxiliary digraph for some larger index, then there is no path. So there's no augmenting path from X. And so we just, for every X, we take this growing set, we take the union of it, and they take the union of all of them. And some calculation shows that it is a non-trivial wave. And one of the technical lemmas ensured that we can assume without loss of generality that there is no such a non-trivial wave. So at this point, we have a contradiction. Okay, any question at this point? Okay, and then I continue with some applications and conjectures. So the first conjecture is due to Aharoni, and I think it's not published yet. It's about the intersection of more than two matroids, and it makes sense for finite but also for infinite matroids. It says that if we have k many matroids, say arbitrary matroids, finitary matroids, or finite matroids on the common edge set, then we are able to find k-1 common independent sets such that we can partition all of these common independent sets corresponding to the matroids in such a way that if we take the spanning of those sets that are, so in every matroid we take the set of those edges that are sorted to that matroid, then the union of these spans gives the whole edge set. And this conjecture is wide open even for maybe so it is open for 3 finite matroids already. So for k equals 2, it is the same as the Edmonds intersection theorem, but for k equals 3, we do not know anything about it even for finite matroids. And there is a weakening of this conjecture due to Aharoni and Berger. It starts the same way. We have k many matroids on a same edge set, and it says that then there is a common independent set of size at least this expression, and for k equals 2, this expression is exactly what we have in the Edmonds intersection theorem. And it's not obvious why this theorem is weaker than the other, but if one can show that so if this conjecture is true in the finite case, for example, then one of the independent sets from these k-1 independent sets must be big enough to satisfy this bound. And in this case, there is a partial result by Aharoni and Berger for k equals 3. So for k equals 3, it's known to be true. The proof is topological and not easy, and so it's a hard theorem. Okay, I wanted to tell some interesting application of the intersection conjecture. Yeah. So I need to mention an important theorem in infinite graph theory. It is the so-called infinite Menger's theorem. It was known as the Erdős-Menger conjecture for a long time, and then eventually Aharoni and Berger solved it in like 2007, I believe. So this is an infinite generalization of Menger's theorem, capturing the combinatorial structure of the optimal solution instead of just quantities. So the generalization based on quantities is just obvious. So so what it says that if we have some directed graphs, it works with undirected graphs as well. So if we have some digraph and we have two vertex sets, A and B, and then we are able to find a system of pairwise disjoint paths from A to B in such a way that we can pick exactly one vertex from each path, such that the resulting vertex sets covers all the paths from A to B. So it separates from B, separates B from A, we should say. Okay, and it was discovered by Aigner, Horev, Karmazin, and Fröhlich that the undirected version of this conjecture actually can be derived more or less shortly from the Matroid intersection conjecture. And so let's see some details of these applications. So we have an undirected graph, and we have two subsets of the vertex set. And for simplicity, I will assume that they are disjoint. So then we can define two metroids. These metroids will be just simply the cycle metroids after contracting A and B respectively. So we have a situation like this. So we take a common independent set of these two metroids M and N with the property given in the Matroid intersection conjecture. And so in the picture we see this I, this common independent set. And so what we can know about this I? So it must be a forest, first of all, because a cycle would be a circuit in actually both of the metroids. And we also know that every tree of this forests, so there's no tree in this forest that meets more than once with the red edges or meets more than once with the blue edges, because otherwise, after the contraction of these sets, we would have a circuit in one of the metroids. And it means that whenever we have a tree in the forest that meets both A and B, then there is a unique path in that tree which is a path which is an A-B path, so it joins A to B. So in this case, we have these paths, and now we need to find a separation in such a way that we are allowed to choose one vertex from each path, and the resulting vertex set must be a separation. So how we find this separation? And they observed that the bipartition given in the intersection conjecture can be shifted, preserving its properties. in such a way that at the end it looks something like this. I don't want to give the formal definition, but intuitively I believe it's clear. And then we simply, on every path, we just take the vertex where the color is alternating, so the color is switching. And based on the properties of this bipartition of I, it's easy to prove that it is really a separation. And I think, and yeah, I have a question. If somebody knows a proof, a Metroid-related proof of the finite directed Menger theorem, then please tell me or write me about it, because I'm very curious that if it is possible to use like oriented Metroids or something like that to get a Metroidal proof of the directed version of the infinite Menger theorem. But unfortunately, we do not know any such a kind of proof even for finite graphs. And thank you for your attention.
Thank you. Are there any questions?
So you explained what this result means when you apply it in the case of Metroids that come like from the cycle Metroids of graphs. What happens for this other example that you had earlier in the talk with these topological cycle Metroids?
Yeah, it's interesting. Maybe we can get some kind of Menger, some topological version of Menger theorem. So maybe we get, yeah, maybe we can get a Menger theorem in the mod G settings, I would guess. I'm not sure.
Okay, cool.
For your question about Menger's theorem, directed Menger's theorem, have you thought about gamoids?
Yeah, so gamoids are usually not always define a Metroid in the infinite case. Yeah, so.
Okay, but is there a nice proof of the directed Menger using gamoids?
I don't know. In any case, are there any more questions? If not, then thank you again, Attila.
Thank you for the invitation.